Welcome to my talk about low overhead Python application profiling with eBPF. Let's begin. A bit about myself. My name is Yonatan Goldschmidt. I have 6 years of experience as an R&D specialist in the IDF. I like everything about computers and software, and today I'm a team lead at Granulate's Performance Research Department. About Granulate, we enable companies to optimize their workloads, improve performance, and leverage that to reduce costs. And I also like wine, especially in Italy. So why is profiling amazing? It's not a new concept, but it's definitely rising lately. So it's getting easier and easier to apply and use, even in production environments. You gain visibility on which parts of your code consume the most resources, and this helps you to expose interesting performance improvement opportunities. Let's talk about profiler types and focus on Python profilers. We start with deterministic profilers or tracing profilers. They track your program's execution in a deterministic way, for example by instrumenting all code paths, to give deterministic results. They are very common and many types exist. Probably the most well-known one is CProfile, which is included in the Python standard library. And to the right of this slide, we can see the example outputs of it. Now, deterministic profilers are very useful during development, as they are very versatile and can give accurate metrics on function and line of code level. However, their intrusive design, the need to insert instrumentations in code or in the interpreter, makes them possibly introduce high overhead to the code execution. They also might require code changes, for example, to enable or disable the profiler, or require deployment changes. For example, you need to start your application with the profiler script. These reasons make them less suitable for production use, because you do not want to introduce any overhead, and you preferably do not want to make any changes just for the sake of profiling. Now, another profiler type is statistical profilers. These work by taking snapshots or samples of your application every set interval, for example, every 1 millisecond or every microsecond, instead of continuously tracking everything that's happening. Over enough time, the accumulated samples portray an accurate image of your application. One common example is PyPerf, which is a sampling profiler written in Rust. This image also shows one way to visualize the output of PyPerf. It's called a flowing graph, and it tells us the relative execution time of different functions and flows in your application. Now, since these samples can be taken externally, therefore these profilers can be made external to the application, as in not intrusive. Thus, they do not introduce any overhead to the application itself, to some extent. Now, the profiler itself is a program running on the system, so it does introduce some overhead to the system, and we'll talk about that overhead when we finally reach eBPF. Now, since it's not intrusive, we do not need to make any changes to the code or deployment. For example, PyPerf can start profiling any running Python process just by giving it the process ID, which is very convenient. For these reasons, they are much more suitable and safe to use in production. Now, deterministic profilers are generally more versatile in their abilities. So for development environments, when you want to accurately measure a specific functional module, you might want to still use them. Now, that's all for the pre-eBPF era. Now let's see what eBPF brings to the table of profilers. A primer on eBPF, it's a technology that has evolved from the old Berkeley packet filters, which is a mechanism in the kernel that allows the user to define filter programs for sockets, like the one displayed on the screen. It was used mostly for sniffing programs such as TCP-dump. The filter program is essentially a small virtual machine with a set of opcodes and operations that it can perform on packet data. For example, the program displayed here checks if the packet's source IP address or destination IP address is the localhost, and if the source port or the dev port is 80. And you can see on the monitor the assembly instructions, the BPF assembly instructions for that program. Now, years forward, this simple interpreter for user programs has been enhanced with many more APIs that are not limited anymore to packet inspection. Also, the programs can now be attached to virtually any logical point in the kernel, not just to the entry of packets. Together, this makes eBPF the most capable tracing or observability infrastructure on Linux. Here's a short example. To the right, we have the code of an eBPF program called OpenSnoop. It's written in a language called BPF trace, which is later compiled to the same BPF assembly we saw earlier. You can read about BPF trace online. This program hooks onto the open system call and thus intercepts all open calls throughout the system. To the left, you can see a sample output from running it on my box. You can see all sorts of different PIDs and programs opening different files. You can see how relatively easy it is to write this simple code that attaches onto a syscall and traces all calls with throughout the system. And also, I didn't mention the negligible performance effect, which is something that we just didn't have before eBPF. This table describes the difference between standard user code, kernel code, and eBPF. The core thing you need to take from that is that eBPF is safe by design. A verifier mechanism exists, which ensures that only safe programs execute. It also means that eBPF programs are not entitled to do anything they please. For example, they are not able to call arbitrary system calls or perform arbitrary writes to memory. On the other hand, eBPF programs have fast access to resources such as memory. For example, they can access the memory of the currently running Python application much faster than PySpy, which is an external application that has to call to run some system calls in order to read the memory of the Python application. Now let's get back to Python. We needed a low overhead sampling profiler, which can sample at high frequency and can easily profile all Python applications running on the system. Plus, we wanted it to be able to extract native stacks and kernel stacks. PySpy, when not introducing overhead on the application itself, does have some overhead on the system. As I said, it needs to access the Python memory in order to extract stack traces. And it does a lot of syscalls trying to do that, which take time. PySpy simply wasn't fast enough when we needed to profile a large Python application with hundreds of threads at high frequency. So we started looking onto the eBPF approach and quickly found PyPerf, which was posted to BCC as a POC of an eBPF-based Python profiler. By the way, we also found a project called eBPF, which is like PyPerf for Ruby, but that's a different story. So we spent a while and added many new features to PyPerf, trying to make it the best Python sampling profiler. So first of all, we made sure it supports all currently available Python versions. We made it a system-wide profiler. That is, it profiles all running Python applications on the system, unlike PySpy, which works on a per-process basis. If I want to profile 50 Python applications, I need to invoke 50 different PySpys, which then introduce more overhead. With PyPerf, I need to run it just once, and it profiles the entire system. Additionally, we have added logic to extract the native stacks, such as Python extensions, for example, JSON, Pickle, or NumPy, interpreter code, and native libraries. And we also extract kernel stacks, which can be, for example, the system calls your application is making. These features were relatively easy to add over eBPF because PyPerf is eBPF-based, and it would have been much harder, if not impossible, had it been written non-eBPF-based. So here's an example of how it looks. This is a simple Granulate application, and in yellow rectangles we can see the Python frames from the Python application. The purple frames are denoted. The purple frames denote native code, and the orange frames denote kernel code. Together, the combinations of those three portray a very accurate image of the application execution. Now, I've been speaking a lot about native code, which is something that many profilers overlook intentionally, saying that the developer should care about the Python code because they do not have control about the native code anyway. So they should just focus on the Python code, and the native frames and stacks are unwanted noise. However, from our experience, we know that taking the native profile into account is very important when you want to truly understand what's going on and which operations on the Python level are taking the most CPU and time. Therefore, we have invested in making this feature work perfectly in PyPerf. So now we'll do a small exercise. I have this function written here, Can you read its code and guess which operations take the most time? And I'll give you a minute to think, and then we will check out the results. And actually it's recorded, so you can just pause and continue when you're ready. I'll continue now. So here I've cut out the relevant native profile of this function. The bottommost frame is the Python function itself. And all frames above it are the native functions that our Python function func, I've named it, is calling. I've added some arrows to explain which is coming from where. And we can see some things that I originally, after I wrote this, I did not expect the profile to look like that. For example, I did think that the string concatenation, which we can see to the right, taking a relatively large part of the profile, actually it was ranking first. The string concatenation takes a large part. However, I did not expect the car calls to take a large part of the profile. Also, the modulo operator takes a relatively large part of the profile. And I only realized that once I've looked at the native profile. What I'm trying to tell you by that is that once we observe the native profile of even of a simple Python function, we can quickly devise ideas on how to improve the Python code of it. For example, after viewing this profile, I now know that the most important optimization to use is to switch from string concatenation to use string IO. And after doing that, the next thing I would do is probably to cache the results of car. And after that, I would try to avoid the modulo operator. Now the compression, which I was thinking, I thought it would take a large part of the profile, it actually takes almost nothing. You can see it in the middle. It's actually rather small. So you need to profile and you need to look at the native profile in order to truly understand how even a simple Python function divides its execution time. So that's it on PyPerf. I hope the last part was interesting. Now PyPerf is a part of gprofiler, which is our system-wide continuous profiler for production environments. And it supports numerous runtimes, not only Python, but also Java and Go, Rust, Ruby. So check it out. It's open source. So thank you. Feel free to DM or connect on LinkedIn, GitHub, whatever. And please try. It's fun. Try free profiling at gprofiler.io. Thank you.